Да, слышно, все
Окей.
хорошо.
А если... А где он? Рядом с вами сидит? Okay, fine. Uh-huh. So, I want to start this talk with the congratulations to our esteemed colleague Igor Krichever, who just turned 72 2 days ago, and there was a conference in New York in his honor, and he was participating in it, and I hope you join me with this, with congratulations, those of you who didn't do it 2 days ago. Okay. And those who did can also join. That never harms. Yes. So the work I want to talk about is a work of 6 people. It's such a long list. I will not put them on the blackboard, but I will read them again. This is Richard Kenyo, Maxim Kontsevich, Oleg Agiyevetsky, Andrei Poata, Will Savin, and myself. So, say it again. I saw everybody in this list because we were discussing this by Zoom. But some people, yes, joined the team without first contact, without facial contact with some of other authors of the paper. So I will start far away from this, from the main topic of this, main object of this thing, and I will tell you a history of some combinatorial problems, which I also was interested some time ago, and where objects that would be key objects in this talk appeared. So it started with, like in the previous talk, it started with computing some simple partition functions. So you will see that it is totally elementary and problems for the school, or even for mathematical Olympiads. It comes from there. So the first thing which we do as an introductory exercise is to compute the number of Young tables, Young tableaus. What is it? For the reason of that talk, which will be clear later, I would like to know the number of partitions, and I will draw them in this way. So I want to partition. I want to consider partitions like this one here. This is a partition in 4 parts, and what I want. So I want to consider partitions which have at most n positive parts, and to each such partition I would associate a monomial, some x, to the power, so let me call this lambda. This is a partition lambda. So I put here the volume of lambda, means the total area of those 4 columns here. Okay? And then I want to compute sum of those monomials over lambdas, such that lambda is lambda 1 bigger or equal than lambda 2, lambda k, and then we get zeros, and the total number of entries here is n. So I want to consider Young tableaus with k columns. K can go from 0 up to n, and I compute the area of this tableau, and then I want to know this partition function. No. You're right. No. It doesn't contradict because you don't know my notations yet. So this for me would be lambda 1. This is lambda 2, and this is lambda k, lambda 4, and the rest are zeros. Is a function of x. That would be Zn of x. No. No, it is not. No. Верно. А вы думали, что неверно? Так Сергей Петрович отвечал на такого рода вопросы. Да. Вот. Хорошо. Так вот, I switch back to English. I'm sorry. So the answer to that is the following. It is a product from 1 to n, 1 over 1 minus x k so that's this partition function is equal to this expression, right? Which is more or less evident. So how to see, well, you expand this, of course, as sum of various monomials, and to see this, you just consider this would be, okay, maybe I write it here. It is x. So how that would go? It would be x to some power. So let me do it more precisely. So it will be 1 plus x squared plus so on times 1 plus x squared plus x4 plus and so on and so forth. So how to see that every monomial you would get by opening the brackets corresponds to some partition is the following. So you from this part you get x to some r1. From this part you get x squared to r2 and so on. And to this picture it will, so, and here is your r1, here is your r2, and so on. Okay? So indeed this thing is the partition function we are looking for. Is that clear and evident now that I said all those details? Very good. So, fine. The next problem would be to do the same, but in the two-dimensional case. What is two-dimensional case? What is one-dimensional here is this thing. This is one-dimensional thing. This is we consider Young diagrams, and now we want to talk about what is called plane partitions. So I will try to draw a picture once. So there are reasons to go in this opposite unnatural order. So you on this square you draw columns now, like that. That's one that's no, like this. I'm sorry. So you make a grid here. And then to every square here, you assign a height, and this height should decay in direction x and in direction y. So this is the highest column you would get. Then here it would stay next one in this direction, and then you also will get another one there. There. So is that clear what I try to say? For your benefit, I draw another picture for this, but this time we look in this direction. Then you will get a more familiar picture for this object which one would call skyscraper. And so on. Is the picture now clear? So those objects which you see here, which are sitting on that square n1 times n2, those are called plane partitions. So again, you have those heights, like here we have lambda 1, lambda 2 decay, and here we have two-dimensional array of integers, and I also have to decay this way and that way. And one would like also to do the same to compute this partition function of such objects. And this is not at all an easy exercise, and it was done, the formula was obtained by McMahon in 19th century, I believe. He was a famous combinatorials, and his answer to that problem was very nice. Let me, if this is a rectangle n1 times n2, then this partition function, this generating function, if you wish, that n1 n2 is the following product over k1 k2. K1 is running from 0 to n1, k2 from 0 to k2, and here it is the product of what? Of 1 minus x to the power k1 plus k2 minus 1. So, and even this can be generalized, and generalization is worthwhile to mention because hooks would appear in more general formula, the hooks which everyone knows from the representation theory of symmetric group. If one would do the same, see what is right. 0. 0. Right. You decide it between you. See, those might be. It doesn't have to go to the root, so it can stop here. So it should be a generalization of that, and therefore it cannot be otherwise. Okay, but let me also put on the blackboard the generalization of this. Generalization, one would obtain generalization if one would not take just a rectangle, but one would take here a more complicated region. You want to consider those partitions, but not which sits on the rectangle, but which sits on some Young diagram, which sits in the rectangle. Then the formula would change to the following one. Z, now I draw this diagram here. This is symbolic notation for this region here. And then we will have a product again over what? Over points y inside this diagram. This is my delta, this diagram. And here you put a product of 1 over 1 minus x to the hook length of the vertex y. And what this hook length is, if this is y, then you count the number of cells here plus and the number of cells there. In the same way, the numbers, the highest are there, so they have to decay this way, in this direction and in that direction. So it can be here or it can be there. They are not related. See, this guy should be bigger than that one, but those two are not comparable. So this is a very nice generalization, and right. The diagram I am talking about, this is the diagram. This delta is this diagram here. So it's floor of my partition. It's a floor, and over that floor the columns are growing, and the highest are somewhere here, and then they go like that. And in the special case when it is a rectangle, then there is just one guy who is the oldest, the biggest, and then the hooks, of course, are these coordinates, sum of two coordinates minus 1. Very good. And then McMahon made yet another step, and he said, let's consider spatial partitions which are living on three-dimensional, say, parallelepipeds. And then he said that the formula for this should be like that: Z n1, n2, and 3 should be a product again. I will not be very explicit. And here it will be 1 over 1 minus x to the k1 plus k2 plus k3 minus 2. So like there, the hook was the length of those two legs. The vertex counted just once. And in 3D, it should be a three-dimensional hook. And again, you count the number of legs minus 2. And that was his conjecture. And then he started doubting this conjecture. And then it turned out that it is a wrong formula. So to say, there is no nice formula for this object, and nobody knows what this the generating function counts. So this is a generating function, of course. So now you do, instead of this two-dimensional rectangle, you consider a three-dimensional parallelepiped, so one dimension more. So you put the highest number at the most distant vertex, and then it should decay in 3 dimensions. Okay. Okay, so, and indeed, it is true that there is no nice formula for this object. But there is some formula, and I will tell you about this formula. And I believe number 8 is this. It starts from 8, yes. So if you go to the Sloan encyclopedia of the integer sequences, so there is a sequence which is a difference between this and that, and it has first 7 entries 0, and then it is non-zero, and then it goes on, and again nobody knows. This I cannot tell. But I will tell you. In a sense, I will tell you a correct formula for this, and then you have this other formula, so you can compute. Okay, so this maybe I erase, and I tell you how to write such a formula, a generating function for those skyscrapers, I will call them, on various partially ordered sets. So this Young diagram here for me is a partial ordered set. So this is the minimal cell, and those are the 3 maximal cells. Those are 3 maximal cells, and there is a natural partial order on this. So what I'm going to tell you is how to write down those generating functions over general partially ordered sets, but you can think about just Young diagrams, or even you can talk about a rectangle with the partial order, which is lexicographic order. So for any dimension, right. In particular for the 3-dimensional case, there will be some formula you can then So I remind you, this is all introduction. So we are still far from matrices, but they will appear. No, maybe I take it back. So this is the order I'm talking about is this one. This is bigger than that, and bigger than that, and so it's like that. So those are all decaying paths. This is the order I'm talking about. In particular, you can see in particular this order would work. This would be a nice order for us. This is one order, one allowed order. The order is allowed if when you go this way you increase, and if you go that way you also increase. If you just number your cells according to this polygonal line, that ordering would be a legitimate one. So I should not use the word lexicography. Okay, so now how to do this? So the first idea is very naive. So imagine we have a skyscraper here, which is, I will not draw it again, something like that. Okay, so it has columns. And to this, of course, to every such picture, we can associate a Young diagram. How we do this? We take the highest column, and you put it to the right. And then you take the second highest, you put it here. And then you proceed. And you would get a Young diagram, right? So you just list all the entries in non-increasing order, and from the right to left, and then you get a picture I told you. Okay, fine. And we know how to count those guys, right? So there is very simple generating function for them. Would be nice to use it. Okay, but if all the columns are of different heights, then it's fine, right? Then if a diagram has columns which are all different, then of course we can go back in a sense. We just take any allowed ordering here, and we put those columns in this allowed order. So how many orders there are, then that would be the number of skyscrapers we would get from a single one, if the columns are the same, or if all the columns are different. But if some of them are the same, this is a map which has the number of images we get this way would be different for different Young diagrams. So this very nice bird is not going to fly for us. So one should do something more clever. And this is what one should do, is to introduce what will be called pedestals of the skyscrapers. So now this is those pedestals would be the main object of my talk. So what are those pedestals? Should I say pedestal or pedestal? Well, how will you think? I don't know. I will say pedestal to be with Russian tradition. So what are those pedestals? Those are very special skyscrapers. There are very few of them, and you define them as follows. So you begin with fixing a linear order P on your cells, like the one I draw here. So for example, you can take for P this order that I indicated. So you can think that this order is on the whole positive quadrant, and it goes to infinity. So this is the way it increases. Good. So you fix one, not necessarily this, but for example this. And now you take another order, take some other order Q, which is another order on that same set. And it also has to increase this way and that way, but there are many such orders. So let me draw one such. So maybe you go this way, then you go here, then you go like that, and then you proceed. So some other order, some other linear order consistent with increasing this way and increasing that way. Good. And now you compare those two orders. So maybe let me draw this order symbolically this way. Those are vertices of my plane listed in the order P. And then I have another order, and that might be like this. So it starts from here again, then it goes here, then maybe it comes there, then it goes back again, and then it goes this way, and so on. So we imagine that at infinity they coincide, so they are different at finitely many places. You can think about infinite, maybe if you are interested in the rectangle, maybe you are interested in just a rectangle, then you on rectangle it is just this picture. So there are two orders here. Both of them starts here because this is the minimal element of our partially ordered set. And this is one linear order, this is another one, and we want to compare them. And the comparison goes like that. So at this vertex they agree. At this vertex they also agree. I go this way and I increase here. This is again a nice step because I made a step to the right, and here I also made a step to the right. But then at this point I see a disagreement, and then I mark it with a star. And then again there is agreement, and so on. And then we make a definition that then what we do, we go along this line and we count number of disagreement that happened before us, before this location. So here happened 0 disagreements, here also 0 disagreements, here there was 1 disagreement before, here is the same one, and again the same one here. So we count how many disagreements happened in the past. Let me say it again. So I make a move, right? From here to here. Now I go to this picture and I see whether those 2 points, whether this one is to the, whether this point is to the right of that one. See, I increase here and I also increase here, right? Then that means that there is no new disagreement. So disagreement comes when here on that picture I make a backward step. So in other words, if I am here, I look to the past and I see how many backward steps I made. Because if I draw my order P this way, that order always go to the right, right? And that one sometimes goes to the right and sometimes goes to back, to the left. So I count the number of, this is what I call disagreement.
Сеня, можно тебя спросить?
Нет, подожди, потому что... Definitely, this is not symmetric. I'm not saying that it is not symmetric, and that is a good point. It will propagate through my talk. This is not symmetric. Да, Гриш?
Если этой паре упорядочений, можно сопоставить перестановку. Верно ли тогда, что число твоих рассогласований есть число инверсий в этой перестановке, или это совсем другое?
Ну, я не могу ответить сразу. Но это, так сказать, это можно проверить, но я у доски не умею проверять. Но во всяком случае определение понятно, да, Гриш?
Не совсем, но я не хочу задерживать.
Сейчас, а мне тоже не совсем понятно. Правильно я понял, что диссогласование — это шаги влево, да?
Да.
То есть мы смотрим... То есть частность их там примерно... То есть их не больше, чем n, например. То есть поэтому это, скажем, не может быть числом инверсий, которое там примерно n квадрат.
Это вот всего точек здесь.
Да, да.
Ну давайте я вот здесь объясню. Вот есть тут порядок, и он как-то выстраивает эти точки. А есть другой порядок. И вот когда я вот этот порядок Q, и скажем по этому порядку Q, вот эта точка, она, скажем, происходит, вот я двигаюсь, а потом я отсюда по порядку Q иду не вот в эту часть, которая больше по P, а в ту, которая меньше по P. Вот такой шаг, если я делаю, то вот это значит, что произошел беспорядок, потому что по порядку Q вот этот шаг это легитимный, а по порядку P он нелегитимный. Видите, мы уменьшаем, значит, функцию P, которая есть отображение из нуля, так сказать, в n. И вот всякий раз, когда такое происходит, мы говорим, что произошел беспорядок, и вот это место помечаем.
Можно я еще тогда спрошу?
Да.
Тогда, продолжая тот же вопрос, и вот, кажется, Миша сказал, что число этих беспорядков не может быть больше, чем n. Может быть, это число спусков, descent перестановки?
Да.
Да. А кто этот человек, который сказал да? Я не вижу.
Ну, я тоже да сказал.
Очень хорошо. И совершенно правильно. Ну вот хорошо. Тогда нет сомнений. Да. Ну вот и хорошо. А теперь вот мы определяем вот этот вот. Now we define this pedestal, which is marked by P and Q, as follows. At location y, it is equal to the number of disagreement before y. So this is a non-decreasing function, right? This is a non-decreasing function, and as such, it is some this is some skyscraper. Y is an element in our delta, a point on this partially ordered set. Y is our partial ordered set. So it can be Young diagram, it can be any other partially ordered set. Very good. So there are finitely many of those, right? Because its height is at most number of points in our partially ordered set. So there are finitely many of those. And then of course there is a generating function, g pedestals of x. Right? It is just sum over p pedestal, and here it is x to the volume of this pedestal p. Okay? And now the key property of those pedestals is the following theorem. So if you want to write P large is the set, this is skyscraper P, which belongs to the P capital, the set of all skyscrapers. There are finitely many skyscrapers which are pedestals. So this is the set, this finite set of those pedestals. There are as many pedestals as there are linear extensions of this of the partial order we have. For example, if we take Q equals P, then this pedestal would be just 0, right? P agrees everywhere with itself. So, значит, смотрите, Q, P, Q по определению вот такой пьедестал. Вот. А? Это не число, это функция. Да, это функция, нет, это функция от y. А y это наша частично. Y is our point in our partially ordered set. And this is a function on this partially ordered set. And I'm claiming that, but it's straightforward to see that this function is non-decreasing on our partial. It's consistent with the partial order. So that means that this is a skyscraper. The set of all such pedestals is P, and then of course it's a small subset of the set of all skyscrapers, which is infinite. Right? The skyscrapers can be arbitrarily high, like the diagrams can go high as much as you want. But the set of pedestals is a finite set defined here. Yes. This is, you're totally right. You're totally right. P. Huh? How many? I don't know. Well, you should know how if the answer is you need to know how many linear orders you can draw on them, and that would be the answer. Probably. But I would not take. Can be. You're probably right, but нет. Берется какое-нибудь P, зафиксированный раз, и Q берутся, да, выбирается какой-то P, и определяется множество вот этих. И с любым другим порядком. Q это все порядки, а P это какой-то порядок. И по вот этому P строится семейство пьедесталов. Будет, далее будет. Далее будет. We will see this later. But thus far it is good. So maybe then this is a bad, it is maybe, okay, let me put it here. Now P, so Sasha would finish what he's saying and then I tell you. So this is P small, this is the set of all pedestals, maybe I put a letter P here. P stands for this fixed order. So this one is fixed. Then for every order I define this pedestal. That definition depends on both P and Q. So this is that same P here, fixed. Now I make a summation over all pedestals defined by this fixed order P capital. And this is the generating function. And now the theorem is the following, that if you want to write down the partition function for the skyscrapers in our partial ordered set delta, then the answer is this one. It's a product of the function g, this is function of x, gp of x times the product, which we already saw, 1 minus 1 over 1 minus x to the L. L goes from 1 to the size of delta. So this is, as you remember, this is a partition, this is generating function of the Young tableaus. So it's a product here, yes, product. you just huh? just a straightforward product. Those are two functions of x, and you multiply those two functions. So if your partially ordered set this is correct, which means that this function does not depend. See, S is a notation. S is a notation for the set of all skyscrapers in delta. So maybe I can erase even this. Once I know delta, then S shouldn't be there. So I was just saying that there are pedestals and there are all skyscrapers. This is an infinite set, this is a finite one. Now if you have your partially ordered set, then you want to know how the partition function, the generating function of skyscrapers living in delta, and the way you should do your computation, you fix some p, you compute this function gp of x, and you then multiply it by the generating function of the Young diagrams. Which means in particular that this function does not depend on p. Okay, if I am saying you that this is a product, then probably there should be a bijection between what and what, between the set of all Young diagrams with the number of columns at most delta capital, and the set of all pedestals. There is a bijection between this and this set, all skyscrapers living on delta. And indeed, there is such a bijection. So I was telling you that there is a map from here to here, but this is trivial but not interesting map. But there is a bijection between the product of those two sets and this and the set of all skyscrapers. And let me write it in one direction, and it goes like that. So you take your Young diagram, some diagram, and you also take some pedestal. Maybe let me keep this p. Let me keep that p, because that set depends on this fixed order. And then the map goes as follows. So you take your pedestal here, which was denoted by p. It also corresponds to some order q, right? We got this p. We got some ordering, some order consistent with p, and then there was a procedure how one defines this pedestal. Okay, and then what you should do is you take your Young diagram. Let me say it in words. You then draw it on your delta according to the order q. That is, you already have some skyscraper, and then you have another skyscraper. So you took an element here, you take an order, you draw your diagram along this q, and then there is this other skyscraper. Those you should add this skyscraper with the one you just obtained as a function of two variables, as a function on delta. This is the bijection. It respects the volume. Is it clear what I just said? If not, I can repeat in a different order if you wish. But I am talking about arbitrary partially ordered set. But you can imagine that I am there, for example. So once again, so how to make a bijection from the product to here? Let's take an arbitrary Young diagram. like this one. And let's take an arbitrary pedestal. What is pedestal? P, letter P, this fixed linear order is here. And every pedestal corresponds to some arbitrary other order on the same set delta. Let it be Q. So this is a Q, and this is a pedestal which is itself a small skyscraper from that set. Good. Now, first of all, I construct some preliminary skyscraper. Like I was telling you, I take this Young diagram and I put it along this order, which gives some skyscraper there. But this is not all. There is also this other pedestal, which is also a skyscraper. It's a skyscraper, which is another function on my set delta. I should add those two functions. So the total skyscraper that I will get will have a volume. That would be the number of cells here plus the number of cubes here. This is the bijection. And the opposite one can also be defined. This is an arrow from the left to the right. This can also be explained, but maybe believe me, that's so. There is a.
Can I ask a question?
There is an old paper of mine in Успехи математических наук where this is explained, and I have very few, maybe two there. So there it is written this way and that way. The question?
The question is when. Is it possible that for two different linear orders to have the same pedestal?
Yes, the answer is yes.
Then when you consider pi set of pedestal, is it a set or multi-set?
So,
I mean, the definition of bijection, you assign Q to some pedestal. So if it is not unique, then...
So when this set here, your question probably is how many elements is there? The number of elements here is the number of, coincides with number of all possible orders Q. If two different Qs give you the same pedestal, that means that you counted twice. So can it be what I'm saying? Yes, it is. That's how it is. Because see, pedestal is defined by the order, and then you might have two different orders with the same pedestal, but still you put your Young diagram differently, according to a different order. Good. So that rested for a while in such a way. And let me repeat it again. So from that formula alone, it follows that this function does not depend on the choice of the order P. Okay, and then, so in a sense, I told you everything one needs to check the three-dimensional Mahon formula. You take a box 2 by 2 by 2. And you compute this polynomial. It is a polynomial of 16th degree. And you compute this series, and you multiply them, and then you take the Mahon formula for this box 2 by 2 by 2, which he conjectured, and then you see that they start to be different. And then there is another thing I want to say. So if we go back to this formula here, so then we can, let us compare it, this formula with that one. So maybe we don't even need to write it. So we have an identity here. So this is this Mahon formula for general delta. This is the same as delta. And this is another formula for the same object, right? Yet I take delta, I take some partially ordered set, some, say, Young diagram, two-dimensional Young diagram. This is the Mac-Mahon formula, which counts the number of skyscrapers living on that diagram. And this is a formula which counts the same thing here. In particular, you can multiply both the left-hand side and the right-hand side by this polynomial here. And then you see that, this polynomial here, maybe I don't know what to do. If you take this polynomial here and you put it here, then you see that there is a ratio of two polynomials. And you see that actually there is a cancellation here because the ratio is again a polynomial. So you might, it is not totally evident. It is not evident that you would have a cancellation here. But that's the fact. And you don't have a cancellation in three-dimensional case. So you take this formula for the three-dimensional case. So the Mac-Mahon, his hope was that you get something like this. But no, there is no cancellation. So you might say that there is no formula for the three-dimensional case, at least no nice formula. So there is an ugly polynomial divided by this other polynomial. That's good. So it depends. You see, it depends on the partially ordered set. For example, when this set is a cube 2 by 2 by 2, then the degree of this polynomial is 16. See, the polynomial does not depend on the order, as you see from this formula. I don't know such a fast way. I don't. But see, in the two-dimensional case, you should just compute this ratio. I don't know whether it is fast or not, but you know beforehand that this ratio would, everything would cancel. But why that happens? Okay, so that's fact of life. So I'm almost done with the introduction. So now let me maybe erase everything, because the story about matrices is the story and I will say it maybe just once more, but only once. Because this, so as I told you, this is here what I was talking about was a function of just a single variable. This is a theorem, yes, of my set. Right. And then, but let me draw symbolically this skyscraper, this pedestal. So for some time it has height 1, then it has height 2, then it has height 3, and then it has 3, and then it has height 4, right? So instead of just counting its volume, one can associate to a pedestal the whole monomial. So it would be x1 to L1, x2 to L2, and so on, x3 to L3. So that would be a monomial PQR R of this pedestal. This pedestal, let me remind again, it is defined by fixed linear order and another running order. Those two orders are orders on our poset delta. So to every polynomial, to every pedestal P per Q, we can associate such a monomial. So if I just put x1 to be x, x2 to be x squared, xk to be x to the k, it would just count the volume. But we keep now more information. Very good. Then instead of the function q p of x, we then get a polynomial. Polynomials, let me call it h of, again, p of x1, x2, and so on. Okay, so before it was just this function, and now it is a polynomial of several variables. And then later we prove with Oleg Givetsky that this polynomial also does not depend on p. Okay. So before we had just one function, a single variable, and now we have a polynomial of several variables. So we keep, so that one, so to say, keeps more information. P это, я забыл, что было такое G. Да, извините, это G, да. Да. Простите, да. Да. Вот эта функция GP, она не зависела от P, так что можно было бы и стереть. Но мы теперь, так сказать, возвращаемся, и вместо того, чтобы сказать, мы пишем x в степени объем этого самого пьедестала, мы говорим, какой объем вот самой первой ступеньки, какой объем следующей и так далее. Ну, во всяком случае, закодируем эту информацию. И вот этот полином, он тоже, значит, не зависит от буквы π. Такой универсальный, такой полином от нескольких переменных, который соответствует, значит, просто всякому частичному порядочному множеству можно сопоставить такой полином. Ну, это замечание в сторону, а теперь начинается матрица. Если уже есть у нас так, yes. So the theorem is written in English. This polynomial does not depend on p, so you can just denote it by h of x1, x2, and so on. This I cannot say. See, for example, if p is linearly ordered, then it can have different lengths, but this would be just trivial. It would be so. Okay, now there is, of course, the most natural thing now would be the following. We have these monomials, right, indexed. So what is this R? So this monomial, you write down this monomial once you have order P and another order Q, right? To every two orders, linear orders on your partially ordered set delta, you write down such a monomial. Okay, once you do this, you can of course write down matrix which corresponds to this picture, right? So the columns are indexed by orders P, and and the rows are indexed by orders q. Okay, so it's a matrix, size of which is the number of linear orders you can put on your partially ordered set delta, and every cell is a polynomial, a monomial like that. And once you have this and you have your Mathematica running on your computer, the natural thing is that you compute the eigenvalues, right? So, and Oleg Agivetsky did this from several deltas. And each time he found the eigenvalues are all polynomials in those letters, x1, x2, and so on. So he made several tries, and each time he found that all the eigenvalues are, again, polynomials of those. The entries are monomials, yes. To every skyscraper, you correspond to such a monomial. So this matrix has a property, which I was talking about here. If you take the sum over the rows, they are the same. At every row, it is the same sum. So you can call it stochastic, so to say. Like for the Markov chain, the matrix of transition probabilities is such that at every row it is 1, right? But here it is the same polynomial. Well, you can, but this is, you might amuse yourself calling this matrix stochastic. But I warn you that in general, it is not a symmetric matrix. Like for Markov chains, it is also not, this transition matrix does not need to be symmetric. So this one is not symmetric. So I don't know whether I understood the question correctly, but from what I told you, actually, because it is stochastic matrix, we know, right, that the eigenvalues, the left eigenvalues and the right eigenvalues are the same. And this is a stochastic matrix, so a vector from all ones is an eigenvector, either right one or left one, but it is an eigenvector. So this polynomial is one of the eigenvalues of this matrix. But all other eigenvalues are also polynomials. And this is cries for explanation, right? And this is what we were able to get. So I don't know whether you can call it explanation or a proof, but the proof of that fact exists. But whether that, okay. Well,
is there any illustrative example?
Huh?
Is there any example which illustrates something?
Sure, there are examples. How big example you want? This is the biggest one.
I see a piece of paper of standard size.
See, this is the matrix. I don't know. It's 16 by 16, all with polynomials, and there are eigenvalues here. Yes, but and then you come tomorrow to see this. Okay, so the simplest example which Oleg computed for this draft is a partition 3-2. So this is a partially ordered set which looks like that. Okay, and there are, this is delta, yes. Believe it or not, this delta has 5 linear orders. So the matrix you get is 5 by 5 matrix, 25 monomials. You want to see them. Serежа, you want to see 25 monomials in this case. So this matrix A has 25 monomials, x1 cube, x2 cube, x1 squared, x2, and so on. And there are 4 more rows like that. And then you do some change of variables to write some monomials. You denote as some letters. And then it turns out that other rows are just permutation of the first one, but of course not all permutations. Some permutations you make, and then there are eigenvalues. There are 5 polynomials here. So maybe this is all I can tell you about this example. If you don't see, if I would do it on my laptop, then you would be able to appreciate those.
Do these polynomials have integer coefficients?
Yes, exactly. That's the point. Those polynomials are polynomials with integer coefficients. This I didn't say, but they are.
But not positive.
No. Not all of them are positive. Okay, now no. It's strange object. No, they are not cyclic. No. Some permutations. Right, that's correct. But there are far more permutations than are used here. Okay. Now now the explanation of all this goes like in the anecdote, which let me tell you now. So some guy comes to the circus and he is telling him, he shows the trick that the monkey is singing and the crocodile is playing piano. And then the question is, the director asks how this is possible, and he finally tells the answer. The truth is that monkey just opened the mouth, and the crocodile is playing and singing. So in a sense, I would say it's the same here. So the reason why all those matrices have integer, I would call eigenvalues, I mean polynomials with integer coefficients, is the following: that each such matrix can be by conjugation with integer matrix brought to upper diagonal form. And that's it. So if you have an upper diagonal matrix, then it's easy to compute eigenvalues, and that is what happens here. So the remark is that, well, there is a road, you do some simplification, some transformation, you write some identities, and then finally you get to a position when it is evident that all the matrices that you are getting here can be brought into upper diagonal form. That's why the eigenvalues are by some conjugation with integer matrices. Yes, U inverse. Yes. You mean no order at all? That would be a special case. Yes. there is no, I don't see, you don't need any analytics here. In fact, this is one step of the reduction. So one shows at a certain moment that it's enough to consider only partial ordered set with no order at all. That's how it comes. So if you want, I can tell you steps, how you do those reductions. Right. Totally true. Right. But see, so maybe I say few more words, and then you will see there are complicated steps there in the reductions. Which let me maybe make one or two for you to. Maybe I list them. So the first thing to do is to introduce a new notion, which is filtration. Filtration of a partially ordered set. F. Okay? So what is a filtration? So let me draw my partially ordered set. Let me do it like this. So let me imagine this is my partial order. Okay, so if you go to the right, you increase. So this is a partially ordered set with 7 elements. Right. I'm saying this way you increase. Now, a filtration is могу стереть. Сейчас это как-то называется. Вот, да, есть непосредственный. Да, вот если это стереть, будет хас. А если это не стирать, будет partially ordered set. Что других? Ладно, хорошо. Ладно. Легче стереть одно, чем нарисовать много. Да. Хорошо. Вот. Что такое filtration? Filtration это вот вы так берете и рисуете. Yes. Filtration is this thing. You say here is 0, here is 1, here is 2, here is 3. So you just map your delta. You map your delta surjectively to some set 1, 2, L, and L is less than or equal to the number of elements of delta. And you want this to be increasing map. So like here. Okay, so this is a filtration. Very good. Now see, I said everything. So that should be an increasing map. So every element here should be higher than every element there. Not lower, exactly. Right. Very good. Now imagine we have some linear order on delta. On delta. And let me have some filtration F. Then I can define another linear order on this. Let me see what is the notation for this other linear order. Yes. So I have P and F. I define a new linear order Q as it was before. It depends on P and on F. I can write it, and I also can say it in words. So see, there are three regions here. So if my two elements sits in the same region, then I just take the relation P between them. And if they are in different regions, then I take F between them. So this is the way you define, once you have F and P, you define Q. And for a given P and a given F, there is exactly one such Q, by the way. Well, it's uniquely defined. Okay, good. And there are many Fs, many different Fs. So again, we can make a matrix, right? We can consider a matrix F. This matrix, it had no notation. Let me call this matrix H, say, of delta. This is matrix of monomials. Okay, but I also can consider also a matrix H of with the index F of P and Q. Let it be M. It's MF. That would be M delta, and there is MF, maybe F delta also. So it's a matrix again. Maybe I was too fast. Okay, so let me. For every F, yes, for every F, I can define such a matrix. And then what I can, let me go back to this M delta and say M delta, well, it can be written in the following way. I sum over all possible. So there are monomials here, and as I told you, every monomial enters into every row, maybe even several times. So I can write it like this. I put here this monomial, x1, alpha 1, x2, alpha 2, and so on. And then I put here a matrix B, alpha 1, alpha 2, and so on. And this matrix B has zeros and ones, entries zeros and ones, exactly where you see this given monomial sitting. Okay, and this other matrix, now I define it also to have entries 0 and 1. Namely, for every P, I look, so I have my matrix P, here is P, somewhere there is this staying this order Q of P and F. F is fixed, and there is and I put 1 in this row. The row is P, and the column is where this Q is this order which is defined by P and F. Okay. Now the point is that each such matrix B, alpha 1, alpha 2, and so on, can be written as a sum, alternating sum of those matrix MF. Maybe I put here plus minus. So every single matrix that we are interested in can be written down in this way. And if we would be able to show that every MF can be taken to an upper triangular form, then we are done, right? So maybe I will not explain this part. This is a tricky statement, but it's an identity. It's an identity, and you do some inclusion exclusion. It's delicate observation, but it's an identity. So if you know this fact, then you go and you check. It's by inclusion exclusion. There is sum over different filtrations, and so you see this one can be upper triangular because every such matrix can be made upper triangular, and this can be made upper triangular because this guy can be made upper triangular by one and the same conjugation. After conjugation, they become целочисленные. Да, не зависит от иксов. И от f не зависит. Да. Против лома нет приема. Вот. Ну вот давайте скажем, а сколько времени уже? А? Half past 6. So okay, so we are in good shape, but we should not. Introduction is finished already for some short time. Да, это уже числовые матрицы, из нулей и единичек, собственно говоря. Да. Вот.
Can you repeat definition of MF?
Definition of MF is the following. So it's a matrix indexed by pair of linear orders. So you take an order P, capital, and you take a filtration F. Once you have those two objects, you can define a new linear order, Q, which is a function of P and F. The definition is I said it in words, let me repeat the words. So this filtration partition my set delta into here in three parts. Now there is an order P here, and there is an order here, and there is an order here, which is the order. I restrict P to here, and to here, and I define Q to be the order P in every such part. I say that the two elements are less than or equal to each other if they are less than or equal in the order P. This is in every such part. And then I say the order Q is such that every guy here in the part 1 is less than every guy in part 2. That's the definition of the order Q. No. Of course, see the just cardinality. By cardinality, you see that the answer is no. It's the number of linear orders here, and this is a square matrix, so you get some Q's. Well, for every F you can do this. You mean in all the totality? cannot tell you. I don't know. Okay, and the remark is that this M has just a single one in a row. In every row there is a single term by definition. Good. So we want to see that those matrix MFs, those can be simultaneously brought to upper triangular form. Good. But remember there is this set delta here, so all depends on delta. But let us consider a special delta which has no relations at all. So the set of relations is empty. Okay, nobody is related to nobody else. Just a discrete set, so it has maximally possible number of linear orders. And of course, those matrices that we're talking about, those MF deltas, of course, those are submatrices. This is a submatrix of M, F, and let me put empty set, meaning that an ordered set with that many elements and with no relations. It's a bigger set, a bit bigger matrix, and this one is a submatrix of that one, right? Imagine that this matrix actually sits in the upper left corner, right? We can renumerate the things. So here it sits M, F, delta, and this one, and this bigger one is MF0, MF empty. Now my remark is that actually this is a block of this matrix. And why is this? Because as I told you, in every row of that matrix there is exactly one single unit, which means that here it is 0, right? Because that matrix also has a property that every row contains exactly one unit, but this one already has the unit, and therefore this is a block of this one. Therefore we would be done if we would show that those matrices can be brought to upper diagonal form simultaneously for every F, which is filtration on an empty set. Okay, since we are almost done, we need we do still yet another step. So and this is even, we will take now even a much bigger matrix, because I was telling you about filtration. Now comes tournaments. Tournaments is the following. Filtration was, as I told you, was a map which we, well, it puts, the filtration puts some order on bonds, on elements of your set. Now tournament is the following. You take your set of vertices, you put bonds everywhere, and on every bond you put the order independently of any other bonds. So this is a tournament is you have much more tournaments than you have filtrations. You just put on every bond independently the order between two vertices. Very good. And again, if you have a tournament T and you have a filtration F, then you can define T prime of T and F in the following way. You have your set, and filtration is just a map now. And if the two sides are in the same layer, then you keep the relations as it was. So you define T prime by knowing T and F in the following way. You have those stratas. So in each strata, the tournament is the same as T. And between stratas, you say that those guys are smaller than those other guys in the tournament. On every bond here, you just keep the relation it was there. And then between this and that, you always say that the tournament goes this way. This is earlier than that one. Now, and then, so we then have now even bigger matrices T of those two tournaments, and for every filtration and for every T, we define the T prime. And again, this matrix has all zeros and one in every row. But this matrix, because of the independence of what tournament is a tensor product of matrices 2 by 2. Because every bond, well, is a pair of bonds so there are just 3 filtrations, right? Three filtrations between on a bond of with two vertices. So there are 3 possible matrices of size 2 by 2, which one needs to analyze. And those 3 matrices are the following matrices. So the 3 possible 2 by 2 matrices according to 3 possible Fs are the following. One is 1, 1, 0, 0. The second one is 1, 1, 0, 0. And the third possible is 0, 0, 1, 1. Now, there is a matrix conjugation with which makes every one of those 3 upper diagonal. The matrix is by which you should make the conjugation is 1 minus 1, 1, 1. This is a discrete Fourier transform. So if you conjugate every one of those by this one, and you get upper triangular matrix. That's the end of the proof. А? Это ничего. Но это ничего. Корень из 2 на корень из 2 будет 2. Сейчас. Так, а у нее детерминант равен 2. У нее детерминант равен 2 у этой матрицы. Это ничего. Мне надо, чтобы все в целом снова было целочисленно. У кого образ? Да. Что здесь и говорится? Да, можно так сказать. А, другая, другую можно взять. Ну, можно, наверное. Вот. Я только хочу сказать, видите, вот yes, but so the last but the bigger matrix, one should take tensor product of those, but in various orders. So at every position you can choose one of the three. So there are many you're getting indeed huge amount of matrices, but all of them go to upper triangular because those three elements do. So I don't know whether this demystify the mystery, or I don't know how it is said in Master and Margaret. Это разоблачение, фокус разоблачен или нет, I cannot say. Да. То есть, so the proof is that I prove more than I promised. But the bigger the object you get, the simpler it is, and the final one is huge but elementary. Sorry? Yes, on the table. So for it is the text with 6 authors is as hard to write as a book of a single author, because the length of the book makes the work increase as a square root of the volume, and 6 people may also make it maybe cubic, the time of work. So the proof is there was a place which I have not explained, but all the statements that I made and all the needed statements for that are contained in that manuscript. I can forward it to the people interested, but you should not distribute it because this is yet a work in progress. So maybe you write me a letter and I will immediately send you a copy. Yes, let me be more precise. The formula that I can present is a formula for a given three-dimensional body. Say you take a cube 2 by 2 by 2, and you want to know the skyscrapers which grow on that box. So it has 16 columns, right? And there should be certain order on that. For this, this generating function is written in this paper of mine in Успехи, and it has two parts, as I explained. The first one is 1 over product of 1 over 1 minus x to the k, and k goes from 1 to 8, and there is times the polynomial. This polynomial is explicitly written there. It's a polynomial of 16 degrees with positive integer coefficients. So it is, it is there, and it is, so to say, it's a finite computation. You have this 16 points. This is this partially ordered set of vertices of a three-dimensional cube. So it's eight points, and then you compute all the pedestals there with their volumes, and you get the generating function of those pedestals, which is a polynomial of degree 8. Degree 8. Okay, I said 16, but в успехах? Это я могу сказать. Я тебе скажу точно. Это работа, где эти подразделения. Это в 2001 года. Называется «Конструкции Вульфа в статистической механике и комбинаторике». Хорошо. Недавняя работа, 2001 года.